All right, so let's revisit our question. What did we do in chapter 10? Correlation. What is correlation? That is the measure of association and the amount of relation, whatever. Measure of association between two variables. Yes, sir. Come again. I was singing over the weekend. Yeah. So we said you can measure the type and then the amount of relationship. Shh. My voice is already hurting, so I'm begging you. And so we said relationship can be positive, negative, or sometimes you can't even tell. So how do we know it's positive? One, you can draw a scatter plot. So that was the first example we did, right? That is going to be on the test. And then we said, you can also compute correlation coefficient, which is R. I gave you that beautiful formula. So we did a lot. Don't worry, we'll go through another example. It will make it a little bit easy for you. Okay. Yeah. So you substitute the values in there and find R. Now, the value of R must be between -1 and 1. So if R is 0, no association, whatever R is, you can tell whether it's positive or negative. From there, we talk about the R square. What was the R square? Coefficient of determination. Yep. I haven't explained coefficient of determination yet. Wait. So I'll give the interpretation later. Now, I believe the next question on the from your book is test the significance of R, right? Good. Yeah, at alpha equals that. We're going to talk about all of that now. So you remember I told you earlier on that when we started the class that sometimes you may have what we call the sample data. Sample data does not represent the population because the population is unknown. But as a statistician, we should be able to find that relationship, that link between the sample and then the population because the population is unknown. That's why I give you X bar and mu. And then we said, okay, from now, we can be using these two interchangeably. We can use a mu or X bar. Then we got to the standard deviation. We said it could be S or sigma. We're going to use that interchangeably. When you get to chapter 10, we have a similar thing going on. So in chapter 10, we computed R, which is the sample correlation coefficient. Now, the population correlation coefficient is given by this letter. It's called rho. It looks like a P. R-H-O. Rho. This is the population correlation coefficient, which tells us whether there's something going on between two variables or not. But since we don't know this, we said, why don't we compute R? So technically what we're saying is, R is the same as the rho. But how will we know whether R can truly represent the rho? That is what question 4 is all about. So we are going to test the significance of R. Is it really true that this R, which we just computed, tells us the measure or the type of association between income and saving? Remember the question was about income and savings? Is it really true that the more you earn, the more you save? I don't know. Because R suggests so. R was 0.96 whatever. Is it 963 or whatever? 963, yeah. Which means that we have a high positive association. But the question is it true?
Wait, did you say that was question number 4?
Which one? No.
It's question number 4.
Question number 4 from that. Yeah, so we are talking about... No, we're not there yet. Question 4 is still part. Now, I want you to understand the concept of number 4 before we do it. For example, the police walks in now and arrest me. What did I do? Yesterday night, I saw you committing a crime. Is that true? I don't know. Maybe another person saw me. But who's going to pass judgment is the court. So they take me to court. It's either they set me free Or probably they believe the police story and then incarcerate me, put me behind bars. You get it? But until proven so, I'm still in the hands of the police. That is what is going on here. R is 0.9. Oh, there's a positive association. Is it true? We don't know. So we're kind of in a court. We want to test it to see whether this is true or, oh, it's just a mirage. Last time we talked about mirage, right? Yeah, it's just throwing dust into our eyes, making us believe that, oh, these two guys are not talking. But when you get closer to them, man, they are the best of friends. It happens all the time. People give you false information, especially when you even start a new job. You see that guy there, he's that. You see that lady there, he's this. But with time, when you stay in the job, like, oh, really? Everything they told me doesn't hold water. Does that make sense? So you kind of form your own judgment. And that's what you want to do with question number 4. So far, so good? In that case, we are torn between two things. It's either R is good or R is bad. Does that make sense? We're saying that R is 0.963, positive association. But is it really true? It's either yes or no. So we're going to set up two hypotheses. One saying, yes, R is good. The other saying, no, this is not good. Let's not work with it. And then we work around it to choose one of them. Does that make sense? That's what happened in the court of law. So this chapter, in the kind of way, is like putting us in the court of law, making us make a decision. So you are part of the jury. You are a juror. We will make a decision. Free him. Put him behind bars. Great. So let's start with this. This is how we go about this. So we're starting with HO and H1. These are something new you haven't seen before. HO is called null hypothesis. N-U-L-L-H-Y hypothesis. And this is alternate hypothesis. And to bring this home to you, I think I can go take you back to the Constitution, which states that no one is guilty until proven so. So that statement, which says no one is guilty until proven so, is the null hypothesis. That is the general perception about you and I. As long as we are not in the grips of the police or the law, everybody assumes that you and I, there's nothing wrong. We are clean. No, that's not. But that may not be true. But even though we're walking free, but somebody somewhere is saying, no, don't assume that Francis is guiltless. He did something bad. Let's put him behind bars. So we kind of torn between the two. So HO here, which is the null hypothesis, is telling us that R is 0. And this guy is saying, no, R is worth something. So the only thing I've said now is we have null hypothesis and then alternate hypothesis. So far, so good? And we have to decide between the two. So this is how we state the null hypothesis. You do not have to memorize because it's already on the formula sheet. If you've already printed out the formula sheet, it's there. If you have a copy from the textbook, it is from the textbook. So we're going to look at both of them. Alternate. So HO. No, let me write that in words. I believe that would be better for most of you. HO is saying that there is no association. And then this guy is saying, no, that's not true. There is an association. Now, do you remember that when we said that there is no association, that meant R is equal to 0? So it's the same as writing rho is 0. And if there is an association, then the rho is not 0. Does that make sense? I think that's better. And as I said, you don't have to memorize this. And you only apply this when you want to test the significance of the R or any other thing. We're going to treat this as a topic in chapter 7. That's when we get to decide, is X bar really the same as mu? Is S the same as sigma? We will test all these things Because we're not just going to assume and then walk out of the class. No. O, this is 0. This is rho. And you can also write this as this. R is equal to 0. They are all the same. When we say R is 0, it means there is no association. I gave that to you on the first day of chapter 10, when I first introduced chapter 10 on the first. I mean, was it last week? Yeah, last week. Yeah. There is an association. So far, so good? So we are now between these two, and we're going to test to see whether to go with this guy or that guy. So the question is, how do we do that? Make sense? We'll be using a table from your formula sheet. So take out your formula sheet. All right, so look at this table. This is what I'm referring to as table A6. But I want to explain to you how it works, right? It's called critical values of Pearson correlation coefficient R. So you know it has something to do with correlation coefficient, right? So you don't miss it. What do we call critical values? It's called table values. So when you take a table, like what I have here, I will call this is a table value, right? Table value, table value. But in statistics, we call it critical value. So anytime you hear critical value, it means that they are taking the value from a table. Make sense? I was just explaining that. Simple. Now look at this table. It has 1, 2, 3 columns. And I think the first one, everybody knows that, right? N. N is the count, the number of items. So from our question, what is N? No. 10. N is 10. Is everybody okay? Because we have 10 different values on the table. So N will be 10 somewhere here, right? And then I also gave you an alpha value. Remember the alpha value? Let me explain the alpha to you, but before that, you see that alpha is given here. Alpha is too, yeah, it's tiny. You know, just squint a little bit. And alpha is 0.005. Alpha is 0.01. But what's the meaning of alpha? I want to explain that. It's a simple concept. And it comes over and over in mathematics. We're going to see it at different places, different chapters, but they will give it a different name. It's just like calling New York Apple City or Boston, whatever they call it, Beantown, whatever. Maybe there could be a third name, whatever. And sometimes when you even have friends, instead of calling him Francis, you may have a favorite name, something that you call the person, right? It happens in families. You don't, aliases, a nickname, all these things. Make sense? Great. So that's what we're talking about here. This alpha has so many nicknames in statistics. It's the same thing, but you're going to see different names. So I'm going to explain it now, and then later once it comes out, I will tell them, oh, you remember alpha? This is it here again. Now suppose I tell you that the chances of snowing tonight is 90%. What is the chance that it will not snow? 10%. That 10% is alpha.
Wait. So the chance that it might not be
Awesome.
So if they're both alpha, how does that?
If they are both what?
Because there's two alphas, there's an A and
Yeah, but you'll be given just one. If I give you this one, that means that there's 1% chance that you'll be wrong or your prediction will not come true. 5% chance that your prediction will not come true. You'll be using one at a time, not both of them. Yeah.
That means, one second. That means you given like in the test the significance of R 0.05. So basically, if we look for the number 2,
Which is number 2?
which is compute the correlation coefficient of n and interpret the R. So if we did find the R, which is negative, automatically we can think of it is wrong based on the...
No. If it's negative, it means there's a negative association.
Right.
Yeah.
Equals 0.962.
Yeah, this is a positive association. So don't connect the two yet. We will get there. Now I just want you to understand the table. Because when you are alone and you don't remember, it's one thing. Yes.
So those two alphas that are given, they're not
They are always given. They are not like work out for it. No, it's always given. And for those of you who be doing your PhDs and your master's degree, when you're writing your thesis, you have to choose one of these. Most cases, we go for this. 9%, then 5%. That means that your work is about 95%. Meaning that you are living in a room for error, 5%. So that if somebody questions your data, your work, that, I don't think there's a problem. You can say, well, I work with 95%. I left the room, so probably that 5% is what you're talking about. You cannot make it 100%. You become God. You don't want to take that position to be so perfect. I'm not perfect. You're not perfect. So we always leave room as a statistician for mistakes, for error. Yes.
So is alpha the variable? They have variable for error or?
Room for error. We don't want to call it variable for error because pretty soon we'll be talking about that. That's why I don't want to say that. So that's a room for error. So far, so good. So we understand the table, yeah? So in our case, I gave you 0.5. And n is 10. So what will be the critical value? That's it. So you have to trace n here. And this. We find this. But the question is, what are we supposed to do with that? The process is systematic. Keep this in mind. Very, very important. So we say that test the significance of R, right? How do we test the significance of R? You come to this table. Now, do you remember these two statements? This is why I told you not to memorize it, because it is at the bottom of the table. And you can bring it to the test room. It's here. Test HO, row is 0, row not 0. You have everything on the table. This is not something you have to memorize. So that thing over there, I don't want you to concentrate on that and lose the value of whatever we're trying to press home here. So how do we then make a decision? Right? We're going to make a decision with the computed R. You remember computed R? The one you computed, the one you calculated. And the one we read from the table. We are going to compare the two. So far, so good? Yeah. Question number 2, we computed R to be 0.963. Yeah. From this table, based on the N and the alpha, the R from this table, the table value is 0.6 whatever. Yeah. What did you get? 0.632 there. So what we're saying here is, if you take this critical value and compare with the computed value, you can tell which one is bigger, right? If the one you computed is bigger than this, then you will choose this one. I'm going to write that down for you. But if it is less, then you choose that one. Don't worry, you're going to get it. I expect that. So it's not as if, oh, she doesn't know, I know that. But you're going to get it. Remember R is 0.963, the one you computed, right? Yeah. So I'm going to call it RC, kind of R computed. And then the R from the table, so I'm going to call it RT, like, just so we understand. Or you can write R table, something, so that you don't lose track of that. Is 0.632. So far, so good? Now, if we compare the magnitude of these two numbers, you can tell that this guy here is bigger than that. If this, the one you computed, is bigger than the one from the table, you will say that, let's choose this one. What does this one say? There is an association between the savings and the income. But then if this value had been bigger than that, then we say there is no association. Now, this statement, what I just said, is also written at the bottom of this table. So you do not have to memorize. You don't even need me to write that on the board, but I will. Let's go to the bottom. Look at what it's saying. It says, reject HO You know we have two things here, right? HO and H1. If we say reject this and you have two things, what does that mean? You have two options. You are rejecting one. It means you are going for the second one. Make sense? I have two options, A and B. Oh, reject this guy. Means we're going for that. So that's what is going on. So this one they are saying reject HO. When do we do so? If the absolute value of R, the one you computed, is greater than the critical value. If this value is bigger than that, reject HO. And if you reject it, it means you are going for, oh, there is an association. And you will accept HO when this R is smaller. So this is the decision making. Reject HO when R computed is greater than the R table. I think this is better. I hope it helps.
So whenever your computed value is greater than your table value, there is an association.
There is an association. And here you accept HO whenever the absolute value of R is less than the critical value, which is the R table. We're going to do a lot of examples just so you understand the concept. Otherwise, you go like, what was he talking about? So now I'm going to give you some random numbers, and this is when you pay attention to have a better understanding. Suppose we are given another R, which has nothing to do with this question, right? And you had negative 0.82, and you are told that N is, say, 4, and alpha is 0.01. If this is a computed value, this is telling us that there is a negative association, right? But the question is it really true that this is a negative association? Then you're going to say, wait a minute, I have to do the test for you. So what test are you doing? You want to go to the table and find the critical value, which is the table value, so that you can compare that and this value and tell whether this is really good or bad. So here N is 4, right? And alpha is 0.01. So you look at the table and tell me what the critical value is. 0.990. N is 4. Alpha is 0.01, so it's 0.990. So now this value, which is the critical value, 0.990. So far, so good?
Yep, so I'm sorry, how do I get, is there a way that we identify critical values with a letter or?
Oh, we just call it critical, yeah. That's why I decided to use the R table so that it helps a little. Otherwise, I'll keep on using R and. So this is R table, right? RT, or critical value. And this, we want the absolute value. Do you see the absolute value there? So you remember absolute value from 097? Absolute value, make this positive. So now compare the two. Which one is bigger? R table is bigger. And if R table is bigger, what do we do? You accept. This is what we have over here. If R table is bigger than this, you accept HO. What does it mean to accept HO? No association. So even though on the surface telling us there's a negative association, when you look deeper, you realize that, oh, there's nothing going on between them. Third example.
Yeah. So wait, so does that mean you want the whole calculation or your whole...
You wasted your time. That's what you want to say,
You
yes.
made no mistake basically, or there was no room for error?
There was room for error, so it may mean that you made mistakes along the line, or probably genuinely there's nothing going on. But statistically, you can never say there's nothing going on. We can just conclude that there is no association at this level. Because another person can perform the same work and tell you that there's something going on. But you can say, oh, I left room for error. So probably I made a mistake, and it's acceptable. Somewhere which we don't know. Remember I told you earlier on that in this class we only identify the mistakes, but we can't fix them. That's advanced class. Maybe we'll fix it later. Now, assuming you do another computation, you compute the R. R is now negative 0.582. And then you are told that in that question, n is 15, alpha is 0.05. So you have computed that, but that's not the end. It must go through the test. How do I take this through the test? Oh, let's go to table A6. Using the n, which is always given to you, and alpha, which is also given to you. So using these two parameters, we go to that table and find the critical value. So what will be the critical value? 0.514. So you have 0.514, which is 15, and then the 0.5. So now we're looking at the magnitude of these two numbers. This time, you notice that the computed value is bigger than the table value. If the computed value, the one you compute, is bigger than the one you read from the table, you reject HO. It means that there is an association between them. I think that is good enough. No, absolute value. Yeah. Because at the bottom of the table, everything is there. Reject HO if they absolutely write it in words. Absolute value of that, yeah. That's what I said, don't memorize anything. You just have to understand how to do it. Because once you take out this table during the exams, not necessarily the exams, but when you are out there working and you want to test something, that's why most of the time when you tell people this is what is happening, they want data. Because as a statistician, you have data and you know how to support your claims with data. If you tell me anything, I will ask you, where is the data? If you don't have any data at the back end, forget it. I'm not going for it. That's why when there's an incident, you have the police and all these people going at the forensic scientists trying to get data to put somebody behind bars. And of course, the lawyer of that particular person also be looking around, gathering all the possible information to get his client out of the grips of the law. We'll get there when we get to chapter 7. It's very interesting. We'll talk about cases that are going on presently, and you make up your own judgment, though. Great.
So wait, and there's no association there, correct?
There is, because this number here, R, the computed one, is bigger than the critical value.
Okay, but if I'm looking at that here, it's saying reject HO when R computed value is greater than R table.
Yes. So it means if you reject this, then there is an association.
Oh, okay.
Yeah. So when you reject, there is. But yeah. Yeah, there is no, because you are saying that there is no association. Is that okay?
So what does it mean, like the association? I understand the whole concept.
Like, let's talk about the example at hand, income and savings.
Yeah.
So we said that there is an association, right? So basically what we're saying is the more people earn, the more they save.
So that just
Prove the scientists' assertion that there is an association. But is that really true? No. We have people who are earning 6 digits, but they still borrow. They are still owing. And we have those who do some menial job, but they save. So we cannot say that. And when we get to the end of the chapter, we talk about that. That, yeah, it is believed that there is an association between smoking and cancer. But it doesn't mean that when you smoke, you get cancer. That's all this chapter is all about. So that you don't just go out there and believe in anything you hear. They say it, oh, really? Let's find out. Otherwise, you will accept anything in life. Don't allow anyone to dump stuff on you. Or probably come to class, I tell you nice, bad stuff, and you take it. Why? Because he's professor. You don't want that to happen to you. You sieve it. Take what is good, drop some. Let's talk about regression. Regression. Oh, you already have that? I wrote this on the board the first day. Regression. Yes, we're going to talk about that. Now, regression is given by this equals, did I write B0? Excellent. 1 subscript 1x. Let's try to understand this before we do the numbers. Now, as a statistician, once you establish that there is an association between two variables, probably more, what that means is you can use one to predict the other. And that is what these, how do we call them? Meteorologists? Yeah. The meteorologists do. That's when they can tell us, predict that the snow is coming. They use regression. That is how the budget of most countries are built. Regression. Look at all the parameters. Those who are taking economics, you are going to take a course called econometrics. It's all about regression. What happens if variable is taken out? What happens if GDP goes up? What happens if fuel prices go up? What happens if it goes down? So it's kind of, what happens if we administer Obamacare? What happens if we allow immigration Obama to pass that? So many things. So many factors are going into this. And it's all regression. Because people think that there is a relationship between the expenditure and the passage of the immigration law. A lot of money has to be pumped into it. There's an association. Therefore, they want to make prediction. Is that really true? I don't know. But as a statistician, probably you can figure it out. So far, so good. So let's talk about height and weight. No, let's talk about 1, 2, 3, 1, 2, 3. Pregnancy. Yeah. Because that's a good example. Now, it is believed that babies are supposed to be born after the 9th month. Well, that is roughly around that. So there's a regression line in every hospital computer system. When a baby is born, man, if you haven't been there, that's okay. But ladies, I believe they have kind of come on to that. But it doesn't mean that you have a baby. They take all the measurement, the circumference of the head, length of the limb, everything, and then they throw it into the computer. And then the computer will tell them, keep this baby here for a while, or discharge the parents and the baby. They don't just make that decision. So when you hear that, oh, they are keeping my sister there for about 2 weeks, it's not because they saw the baby and they're like, oh, this baby must stay. No. They have all the data, so there's a regression line. They throw everything in there and it pops up. Let's keep the baby here for observation. That's why they have the antenatal and the postnatal. They do all these measurements. So after 3 months, you take baby back. They do the measurement. If the growth is disproportionate, that's when they begin to identify there's this problem. In America, you have a lot of names. Man, she is this, the baby is whatever. But that's good because it helps them to actually solve this. I mean, whatever it is, put the thing in order. Whatever it is. So that's a good thing. So regression, as we see it on the board as an equation, is out there. It's not in your books. It's everything you want to see in life. So that's what we want to talk about now. Now you have the picture, right? Yeah. Good. B0 and B1 are also given by beautiful formulas. Once again, you do not have to memorize the formulas. I'm going to write the formulas on the board, and I will show you how to do the computation, and then we continue from there. So far, so good? Yeah. Great. So before you compute B0, you must compute B1. So B1 must always be computed first. Make sense? Well, first. You'll get to know why. Summation xy minus summation x times summation y all over n summation x squared minus summation x all squared. This is kind of similar to the first one, but it's a variant of that. But so it's just a formula. It's also on the formula sheet. So you can choose to write it or forget it. If you want me to write it down on the day of a test, I don't mind doing that. Now, the second one is this. B0 is given by y bar minus B1 times X bar. What is X bar? Mean of X. So what would this one be? Mean of Y. And remember we have the Y values, right? So we can find the mean. B1 will come from here. Now let me explain this beautiful thing over here. This is like that. Basically what this means is, oh, I'm hoping that my prediction will be right. That's it. Because your prediction can be wrong. So when you see that little tiny thing on top, it means that your prediction can be way off. But you are hoping. Let it be right. That's why sometimes they will tell you it's going to snow and it doesn't snow. They go off. That's that thing there. If you challenge them, they tell you, oh, we were just hoping. Or probably they say it's not going to snow and all of a sudden, boom. Why didn't you warn us to prepare? Whatever it is. Great. So that is prediction. You're just hoping that your prediction will give you good stuff. And that's what they use to predict the economy, whether the economy is going to do well, it's going to go down, blah, blah, blah. Fuel prices are going up or going down. It's everywhere. Very good. So, yeah, we have the pieces and everything together. Now let's start with the computation, right? Let's start with B1. Now remember you have this information, right? You have all these. So it's not as if I'm creating something. You go back to your table so you know where they are coming from. So B1 will be equal to, what is N? 10 times summation XY. From the table, you have it from last time.
1564.4.
Come again?
1564.4.
Like this? Oh, okay. Minus, what is the sum of X? 463. What is the sum of Y? Thank you. All over. Of course, we know N is 10. What is the sum of the squares of the X's? 23,533 minus 463 square, right? Yep. Now the rest is calculator. If you have a good calculator, one touch. If you don't have a calculator, as I don't, then you have to go through one step at a time, which is waste of time. So get a good calculator. When you multiply these two, the product of these two numbers will be 15644 minus, what is the product of these two numbers? Come on. No calculators in the house? 12,639.9. Thank you. In the bottom, we have 235330 minus, what is the square of 463? 214,369. So far, so good. I haven't done any. 128? 86?
Yeah. Oh, I just did
86? Okay.
Yes, 126.
Like that? Good. That's why we're working together. Everything okay from there, right? Now, why don't you find the difference between these two numbers? I will put it on the other side. So we're still computing B1. Don't forget that. Now, what is the difference between the two numbers? What will be the numerator? Two. Like this? Over.
2957.4.
Oh. Over the bottom. 20.
No, 200. 2069. 69.1. I mean, 1. No, take point off. Take point off.
It's a whole number, just 9 at the end.
Yeah, 61.
Like that. Oh. Like this? Okay, I had 0.1 and point whatever. Now divide the two. 0.141. 3 decimal places is good enough. Is that okay? Now let me tell you something which is very, very important. And if I say very, very important, that means it's very, very, very important. Oh, you smart. All right. Now, you remember R for this particular question. It was R 0.963, right? You see this is positive. What happens to the B? B is also positive. Now, the B is also called the slope. You remember slope from 097? You know the slope determines the direction of a line. If the slope is positive, it goes up. That's why when we drew the scatter plot, the line was going up because the slope was positive. This is positive. Whenever the slope is positive, correlation is positive. If this is negative, this is going to be negative. It's an important statement in mathematics. So keep that in mind. Well, when the correlation is positive, slope is positive. When this is negative, the other is also negative. They are kind of the same. You cannot get one to be positive and the other to be negative. That means there is something wrong. Check, fix it, and continue.
So a negative number there equals a negative slope.
You mean if this were to be a negative number?
If that were the negative number.
Then you have a negative slope, meaning when you plot it, the line should be going down. And if the slope is negative, that presupposes that the correlation is also negative. That's how they are related. All right, now let's try B0. B0 is y bar minus B1 x bar. How do we find y bar? The mean of the y. The mean of the y is adding all the y's and dividing by 10. And I think we already have the sum of the y at the bottom of the table. So we have 27.4 over 10, which is the y bar. Yeah? Minus B1. That is what we just computed. 0.141 times x bar. 463 over 10. Now this is the same as 2.74 minus 0.141 times 46.3. Any questions on these? Calculator will give you that. This is 2.74 minus, what is the product of these two numbers? 5283. Now find the difference between them. Negative 3.788. Let's make it 88. So we have B0 now and B1. So what you do is you substitute that into the equation, and that will give you the regression equation. So y bar is equal to B0, which is negative 3.788, plus B1, which is 0.141x. Let's see. This is the linear regression line. And the linear regression line is kind of similar to what you did in 097, where you said y is equal to mx plus b. Remember that? When you find the slope and the y-intercept, you substitute everything into it for you to get an equation. So if you compute B0 and B1 and you do not substitute that here, you know you are off because you don't actually have the regression line. Now, this regression line is what we use for prediction. So we've already established from question number 4 that R is significant, that there is an association between the two. So we can use one to predict the other. Does that make sense? So the next question, which is going to be probably the last one, is that a 6 question? 6 questions is the last one, right? Oh, how nice. So what will happen on Thursday is Thursday, we will go through a similar example to what you've done today. And I believe if you are missing anything, you should have a better understanding. Then I may start with chapter 4 on Thursday. I don't know, but time permitting. But I know we're going to be over, chapter 10 will be over with today. Almost done with chapter 10. It's a short one. Very, very important, but short. So let's go to number 6. What does it say? Predict the savings. So, which of the variables represent the savings? You go back to the original table. It's on the table. Don't make things difficult. Go back to the original table. I wrote savings and income, and to each of them you have a variable assigned to it. Excellent. X is income. Everything is in the table. Yep. Everything is in there. Is anybody here who hasn't found it yet? Great. So, predict the savings. What does that mean from this question? Find Y. You can only find Y when X is given. So according to the question, what is X? How do we know that is X? And income is excellent. You get it? Because in that question, there's nothing there stating that, oh, the income is X. But you know from before that income is represented by the variable X. So when they say 60,000, you know that, oh, so this one must go there. But question is, are we going to write a 60,000 in there? Why 60? Because that is how the question stated. It stated earlier on that everything is measured in thousands. You remember that table? And I went over the values with you before I even started that. So the 0.5 means 500. So when you are given 60,000 here, you cannot substitute that in there. You can only write 60. Why are we doing that? Because the question told us to do so. Everything is measured in thousands. It means take out the thousands and substitute 60. Let's do it. So this is question number 6. Y hat is negative 3.788 plus 0.141 times 60, which is negative 3.788. Then you multiply these two. This is PEMDAS. Don't add these two numbers and multiply. You mess up. That is 1, 4. It's going to be 8 point something, yeah? 8.46. And then you combine the two. What does that give us? 4 point whatever. 4.672. So how much did this family save? 4,672. Why? Because everything is measured in thousands. They save 4,000. And you can also throw in your income. Even though this is not a good one or a perfect one, but hey, you can just say, hey, I also earn this amount at the end of each year. How much can I save? Then you can start working towards. This is just, is it February? Yes, second month. You can start saving. That tells you how much you should be able to save. Is that okay? Any questions? Great. The only thing left is question number 3. Coefficient of determination, right?
What is R2?
R squared, right? I did not explain that. We just computed it. And I don't have time. But, no, that's not that.
I have a question. How did you get 4.62?
I added negative 3.788 to 8.46. Yes.
Yeah, I got 4.813.
Anybody had 4.813 or that one?
No.
Two people had this too?
4.672 is correct.
Well, since two people are saying that, I'm taking that. It doesn't mean it's right, but
Yeah, it's right.
I don't know. Maybe check your computation. So, let's reserve that for
Yeah, let's-
Thursday.